This is my second time recording this because the first time I guess it didn't work. So if I sound a little annoyed or if I speed through a certain section, I apologize. But it's going to be a short one no matter what anyway. Yesterday and Monday, you guys reviewed oxidation numbers. It's a very key point or key part of this last unit, redox. But what exactly is a redox reaction? What is this whole unit based on? Well, a redox reaction is short for reduction oxidation, a reaction where electrons are transferred from one substance to another. So electrons are the key. Electrons are going to move from one thing to another thing. Why would electrons want to move? All of your hands would shoot up at this point and say to fulfill that outer shell, right? It's all about that outer shell of electrons. So something is going to gain electrons to fulfill that outer shell. Other things are going to lose electrons to fulfill that outer shell. The key is that the electrons lost must equal the electrons gained. Remember that three things are conserved in chemical reactions: charge, mass, and energy. Here, we really care about charge. So the electrons lost are going to be equal to the electrons gained. So let's take a look at this equation, this reaction. What if we were to assign oxidation numbers to each thing in here? It would be pretty easy. Magnesium is going to be 0. Ag, if we look on the periodic table, has a couple oxidation states, but here it's +1 because chlorine is -1, right? Chlorine is a halogen or a halide, so it's always going to be -1, which means Ag is +1. Ag here is by itself. Any free element, remember those rules, is going to be 0. Again, we know chlorine is -1, which means magnesium is going to be +2. Right? When I write -1 over chlorine is not based on how many chlorines there are. It's based on just the fact that chlorine is a -1. There are 2 of them, meaning that there are 2 -1 charges, or -2 total, and that magnesium has to balance that -2, so it's a +2. So this is just a little review of oxidation numbers from the last 2 days, but I'm going to introduce a new term here, reduction. Reduction is when an atom gains electrons and the oxidation number, quote, reduces. If you're gaining electrons, think about what's happening. Electrons are negatively charged. So reduction is just you're increasing or becoming more negative. Oxidation is when an atom loses electrons and the oxidation number increases, goes up. Again, electrons are negative. You get rid of electrons, you're going to become more positive. Your oxidation number is going to go up. And one of my favorite things in chemistry, as all of you know, are acronyms. So we have another acronym for this unit. It is OIL RIG, O-I-L space R-I-G. There's a reason why there's a space between them. And that's because it stands for oxidation is losing, reduction is gaining. So oxidation relates to losing electrons, reduction relates to gaining electrons. Very, very simple. So how are we going to tell that a redox reaction occurred? Well, we have to determine what's reduced, what's oxidized. So again, all of these red numbers relate to the oxidation numbers or the oxidation state, and we can use those to help us figure out what's reduced and what's oxidized. Again, if we are looking for what's being reduced, we're looking for what is gaining electrons and becoming more negative. Let me underline that. We're looking for something that becomes more negative. So if we look, Mg starts out as 0 and it turns to +2. Is it becoming more negative? Is it gaining electrons? No. So Mg is not being reduced. What about Ag? Ag goes from +1 to 0. It is becoming more negative because, again, its oxidation number is going down. It is gaining 1 electron, and what we do is we write out Ag plus because that's what it started as. We're going to add 1 electron, and that's going to turn into Ag0. So this little reaction right here we call a reduction half reaction. I'm going to go into more depth into that tomorrow and Friday, but I just wanted to introduce it. All it does is it says Ag originally had a positive charge. gains 1 electron. It's being reduced into Ag0. Well, now we have to find out what's being oxidized. And again, oxidized is becoming more positive because you're losing electrons. Oil rig, oxidation is losing. So if we look, Mg goes from 0 to +2. It's becoming more positive. So there you go. The thing being oxidized is Mg because it loses 2 electrons. So it starts out as Mg0. Well, it's releasing 2 electrons. Guys, a key thing that people do here is they'll do Mg0 minus 2 electrons. You have never seen a minus like that in a chemical reaction. You write the 2 electrons on the right. Think about heat. When heat is written on the right, it's given off. The electrons are written on the right. The electrons are being given off. And what's left is Mg plus 2, right? It turns into that Mg plus 2 because it gave away its 2 electrons. So the key takeaway here is oil rig and use the oxidation numbers to determine what's being reduced and what's being oxidized. So if I just gave you a random chemical reaction, right, I'll give you this, chromium oxide plus aluminum going to chromium plus aluminum oxide, and I want you to determine if it's a redox reaction. There's a couple steps you can take. First one is just assign oxidation numbers to all of the atoms in the reaction. If we were to pick out the easiest 2 things to assign oxidation numbers to, it would be aluminum and chromium. Why? Because they're by themselves. If you see something by itself like that, its oxidation number is 0. Simple. One of the rules from the last assignment you guys had to do was that oxygen tends to always be -2. So we can fill that in. Oxygen tends to be -2. Oxygen here is -2, but we have 3 of them, which means in total we have a -6 charge, and we have 2 chromiums to balance that -2 charge, which means that each chromium is +3. Same thing over here, right? Each oxygen is -2. We have 3 of them, so -6 charge in total, which means each aluminum is +3. So we've written all the oxidation numbers. Now we're going to take a look at them and see if anything is gaining electrons or if it's losing electrons. An easy way to do that is to see if any of the oxidation numbers change. If the oxidation numbers change, that tells you something is being reduced or oxidized. If the oxidation numbers don't change, nothing happened, right? No electrons were transferred, gained, lost, blah, blah, blah. So let's take a look. We have chromium starting out at +3. Is anything happening to chromium? Well, it's turning into chromium 0, you can think of it as. So if it's becoming positive, it's going from +3 to 0. Is it becoming more positive or more negative? While it's going down, it's becoming more negative, which means it gained electrons and was reduced. What about oxygen? Oxygen started out as -2 and it ended at -2. Was it oxidized or reduced? No. It stayed the same. It did not change. Which means aluminum is going to be the thing that was oxidized because, let's see, it started out at 0 and it became more positive and on the right side at +3. So it was oxidized, right? It lost 3 electrons, lost 3 negative charges, and became +3. Let's do another one, right? K2S plus 2HCl goes to KCl plus H2S. Let's assign oxidation states. Group 1 atoms, like potassium, are always going to be +1, right? Group 1 is always going to be +1. Hydrogen, 90% of the time, you guys don't have to worry about the other 10%, is going to be +1. And then let's just fill in the rest. Chlorine is nice and easy. Sulfur is nice and easy because let's take a look at sulfur. Sulfur has 2 potassiums bonded to it, right? Each one of those is +1, which means that 1 sulfur needs to balance out 2 positive charges and be -2. Chlorine needs to balance out that +1. It's going to be -1. Likewise over here, going to balance out that +1. It's a -1. And here again, that sulfur is going to be a -2. Don't doesn't matter what the coefficients are in front, by the way. The coefficients, again, is just for balancing of mass. Right now, what we're doing is looking at conserving the charge. Mass is conserved with the numbers in front. The charge is conserved with the oxidation numbers, okay? All right, well, something's off about this equation. We have potassium starting out at +1, ending at +1. Sulfur starting out at -2, ending at -2. Chlorine starting at -1, ending at -1. Hydrogen starting at +1, ending at +1. So there's no change in the oxidation number for any element. Therefore, it's not a redox reaction. There were no transferring, gaining, or losing of electrons. Therefore, it's not a reduction oxidation reaction. And this type of reaction should be familiar to you guys because it's a double replacement. So double replacements are not redox reactions. They are not redox reaction because oxidation numbers don't change. There is no gaining or losing of electrons. So the worksheet that goes along with this PowerPoint is pretty straightforward. Your first step is going to be to say what type of reaction is: single replacement, double replacement, synthesis, decomp, etc. Right? You're going to identify the type of reaction. Then, using oxidation numbers, you have to fill in what was oxidized and what was reduced, if anything. And then in the last box, all you're going to do is say, was it a redox reaction? And then there's one question at the bottom. So again, use these steps. Assign your oxidation numbers, determine what was oxidized or reduced using your oil rig, and then determine if it was a redox reaction based on the other boxes. It's very straightforward. It shouldn't be that hard. If you need any help, again, remind, email. You have multiple ways of contacting me. But I think you guys will do pretty well with this. All right, have a great day, everyone.